All right, let's get started with 1.9. Inverse functions was what we're working on today. So an inverse function is when we flip the x and the y. So if we flip the domain to the range, we end up with an inverse function. So you'll notice here, get the pen. You'll notice here that we have 1, 5, and then we have 5, 1. They're switching. 2, 6, and 6, 2, right? They're switching. So the domain of f becomes the range, right? The range and the domain switch. And this is our notation here. F negative 1, right? We don't say f negative 1. We're going to say the inverse of f. F negative 1 means the inverse of f. All right, so to find an inverse function, we flip the x's and the y's around. All right, so let's see if we can do this. So an inverse function, to switch the x's and the y's around, basically we're canceling out what we're doing to the x. All right, so if we want to find the inverse, one way we could do it is what's called informally. And informally isn't doing any specific algebraic or geometric steps to it. We're kind of just thinking to ourselves, all right, if this is 4 times x, how would we cancel that out? So the opposite of 4 times x, to get rid of that, right, we'd have to divide by 4. So the inverse here, we could kind of informally think about it as x over 4. How do we undo 4 times x? We're going to divide by 4. All right? And so to make sure that we're right, we do need to test this. So we're going to do f of the inverse. So our original f was 4x. Instead of x, we're going to plug in our inverse, x over 4. And the 4's will cancel out, and we do get x. So this one checks. All right? The identity function here, what this is saying, what that means is that if you do the inverse and the original function together, you should be left with just x. They should cancel out everything but the x, which is what we're saying here. Can we cancel out the original? Let's go the other way around and say x over 4. But instead of x, let's plug in the original function, which was 4x. So now we're doing this one. And the 4's do cancel out, and we're left with x. So this one checks as well. All right? So see if you can do the same sort of thinking on exercise 7. Okay, so definition, let f and g be 2 functions so that when you do the f of g of x, you get x, and the reverse, g of f of x turns into x. All right, if that is true, then g of x would be equal to the inverse of f. All right, and so something that's going to come up a lot is that the domain of f is the range of the inverse of f. All right, you're going to switch your domain and ranges. So when we have restrictions later on, you need to keep that in mind. Okay, it won't come up until later. So let's take a look at this. Which of the functions is the inverse of 5 over x minus 2? All right. So we could kind of think informally to ourselves, how are we going to unwrap that? Well, I see a minus here. How do I unwrap a minus? Well, probably a plus. So and the g of x here doesn't have a plus in it, right? We just have a minus. So my first instinct is that it's going to be h, right? And so let's test that and see if h is the winner here. So we can plug this in. Let's go to our original function, 5 over, and instead of x, let's go ahead and plug in this whole thing. So we would have 5 over x plus 2, and then minus 2. All right, so that'd be the setup. The 2's are going to cancel, so now we've got 5 over x. And remember, you never divide a fraction, you multiply the reciprocal, x over 5. The 5's cancel, we're left with x. That's what we're hoping for. H of x is indeed the inverse of f of x. So we could say h of x equals the inverse of x. Write it like that. All right? And it does say which one, so we're going to know that g of x is not the right answer. It was an either-or type of problem. So let's see if we can figure out which one is the correct inverse for exercise 19. All right, so when we talk about graphing inverses, okay, if you graph the original and the inverse, you're going to have a reflection over the line y equals x. So we've talked about reflect over the x, reflect over the y, and now we're going to reflect over the line y equals x, which is this dotted line, 45-degree angle. All right, so if you have something like this, then the reflection would look like this, okay? Mirrored over that diagonal line. It's a little tricky sometimes to see, but I think if you put it in your graphing calculator, it'll make sense. So let's do this one. So I've already in my graphing calculator plugged these equations in, right? 2x minus 3 plugged in here, and 1/2, 0.5, x plus 3. And then I've also plugged in the line y equals x, because that's the line of symmetry that we're going to look at. And so we're going to graph it and just see if that works out. So let's graph. Here comes y1, here comes y2, and here's y equals x. And you can see that that is a perfect mirror one over the other. Okay? So we can just look at it, but really if we want to see it, the x's and the y's should switch, right? In our y1 and y2, if we made a t-table, the x's of one should be the y's of the other, right, in our range. So let's see if that's true. Let's check our table. If we plug 0 in, let me go up here. If I plug in 2, I get 1 in y1, which means that if I plug in 1, I should get 2 in the other one. If I plug in 3, I get 3. So if I plug in 3, I get 3. If I plug in 4, I get 5. So if I plug in 5, I get 4. The x's and y's are switching. So we can use our table to prove this also. All right, so that's how we're doing graphical functions. See if you can do that on exercise 25. All right, example 4, we're going to do the same exact thing here graphically. So let me bring the graphing calculator back. That's not it. There you are, and I'll have to clear out these. Y equals x squared. And there are restrictions here. So x squared, and x has got to be greater than or equal to 0, number 4. And our next line was square root of x. And I'm going to keep the y equals x line. And let's go ahead and graph this. All right, there's x squared. There's square root of x. And look at that nice, clean line here. All right, so I want to go back over here really quickly and just sketch these out. So we had this. We had square root, and we had x squared. Okay, those are symmetric. On here, for the square root of x function, the domain is x has got to be greater than or equal to 0. The range is y has got to be greater than or equal to 0. So knowing that, if we were to flip it, we would take this x and we would say for the other function, x squared, y has got to be greater than or equal to 0. And then flip this one to get x is greater than or equal to 0. Okay? Just a reminder that we're always flipping the domain and range for our inverse functions. So keeping that in mind, try exercise 27. Okay, so you will only have an inverse if you are a one-to-one function. A one-to-one function is when you switch the dependent and the independent variables and they match up. So if you remember, think back to algebra, and you could have something like this, 1, 5, and 2, 5, and 3, 4, and 4, 4, where two different inputs went to the same output. You can't have that for a one-to-one function, right? Every input has to match with an output, and every output has to match with only one input to be a one-to-one function, all right? And if that happens, we pass not only the vertical line test, but the horizontal line test. So x squared is a function because it passes the vertical line test, but it's not a one-to-one function because it wouldn't pass the horizontal line test. Okay? If you don't pass the one-to-one horizontal line test, then you will not have an inverse. All right, so we only have to find inverses if our original function passes the horizontal line test. All right, save yourself some time. All right, so we take a look here. You can see that x cubed minus 1, the first one there, definitely is a one-to-one function and does have an inverse. And then looking there again, it's a quadratic x squared for the second problem. B does not pass the horizontal line test, will not have an inverse. So use that line of thinking. Exercise 39. All right, so now we've done it graphically. We've used our graphing calculator. Now let's figure out how to use algebra to find an inverse. And the key on this is interchange x and y. All right, switch x and y and then solve. All right, so here's our problem. We've got 5 minus 3x over 2. And we all know that f of x is really standing for y, right? So to find the inverse, we're going to swap the x and the y's. So we're just going to rewrite it exactly the same, but everywhere you see x, you write y. Everywhere you see y, you write x. And now we need to get y all by itself again. So let's times by 2. 2x equals 5 minus 3x. I'm sorry, 3y. 2x minus 5 equals negative 3y. And let's divide here. So we have negative 2x plus 5 over 3 equals y. And that is going to be our inverse function. Okay, so switch the x's and the y's and then solve for y. Give it a shot on your own. Problem 63. Again, remember, be checking the answers in the back of the book to make sure you're getting these right. All right, example 7. Let's find the inverse function of this. Now, one thing to be careful of here, just to keep in mind, quick sketch of this, 2x minus 3, we're going to shift right. This is really square root of 2x minus 1.5. So we're shifting right 1.5 before we sketch it, right? If we look at this, let's keep in mind what our domain ranges are. So on this one, x has got to be greater than or equal to 1.5. Y has got to be greater than or equal to 0. Okay, keep that in mind. That's going to come up in a second. Let's find the inverse. We're going to switch this. So we're going to say x equals square root of 2y minus 3. How do we get rid of square roots? We're going to square both sides and get x squared equals 2y minus 3. So x squared plus 3 equals 2y. And divide everything by 2. So we'll get x squared plus 3 all over 2 equals y. There is a restriction on this. X has to be greater than 0. I circled the y because remember the range of 1 is the domain of the other. Okay, and we always want to put our domain restrictions on there. X has to be a positive for this to have a mirror image. Because if we let it be negative, then we would complete the square root, or the squared, the quadratic, and all of a sudden that's not a nice mirror image anymore. So we need to keep the restriction, x is greater than or equal to 0. All right, keep that in mind. Exercise 69. And that's it. Questions, make sure we ask in class.